In the last video, we have proved the following problem. We have shown that if f is a continuous function from the open interval 0, 1 to r, such that the limit for n that goes to infinity of f evaluated at x over n is equal to 0 for every x in the open interval 0, 1, then the limit of the function for x that goes to 0 is 0. Now we want to prove that if we eliminate the hypothesis of continuity for the function, then this statement is false. In other words, we want to find an example of a function of this kind such that it satisfies this hypothesis, but such that the limit of x that goes to 0 of the function is not 0. For example, the limit could not even exist. In order to prove what we want to prove, I will show you some intuition behind the solution to this problem. Suppose that we can find a set D such that it is a subset of the open interval 0, 1, but not equal to the interval 0, 1, such that D is not empty, and such that it satisfies the following properties. For every x in 0, 1, we need that if there is a natural number n such that x over n is in D, then x over m is not in D for every m greater than n. And we also need that 0 is an accumulating point of D, where obviously we are considering the closure of D in R. So this is a closure in R. Now, if we have such a set, the example that shows that this statement is false without the continuity is easy, because we can consider the function f of x that is equal to 1 if x is in D and 0 if x is not in D. Now, take x in 0, 1. There are two options. The first one is that for every n in n, x over n is not in D. In this case, we have that f of x over n is equal to 0 for every n, and so the limit of n that goes to infinity of f of x over n is equal to 0. The other possibility is that there is a natural number such that x over n is in D, but then from this property of the set D, we have that x over m is not in D for every m greater than n. This implies that f of x over m is equal to 0 for every m greater than n, and so this implies that the limit of n that goes to infinity of f of x over n is equal to 0, also in this case. Since we are assuming that 0 is in the closure of the set D, we have that we can find a sequence yn contained in D such that yn tends to 0. But now, since yn is contained in D, we have that f of yn is equal to 1 for every n in n. And so this implies that the limit of x that goes to 0 of f of x cannot be 0. I mean, this limit could not even exist, but if it exists, it cannot be 0. Because we have two cases. If this limit exists, then it cannot be 0. Otherwise, we would have that the limit of n that goes to infinity of f of yn should be 0. But this is a constant sequence, constantly equal to 1. So this cannot be the case. The other possibility is that this limit does not exist, but in this case we don't have to prove anything because we already have that is not true this fact. So the other case that is the case where the limit here does not exist is okay. So now we have a good intuition of some examples, but we to conclude the counterexample, we have to find such a set D. And my idea was the following. Consider D that is equal to 1 over P, where P is a prime. Now, clearly 0 is an accumulating point. Clearly this set is non-empty. This set is not equal to the open interval 0, 1. We only have to check this condition. So, suppose that there is x in 0, 1 and n natural number such that x over n is in D. This implies that there is p prime such that 1 over p is equal to x over n. We want that x over m is not in D for every m strictly greater than n. So, to prove this, suppose by contradiction that we have that x over m is in D for some m greater than n. This implies that we have q prime such that 1 over q is equal to x over m. But then this is equal to x over n times n over m. But x over n is 1 over p, so it is equal to 1 over p times n over m. And so this implies that p times m is equal to q times n. Now, since 1 over q is equal to 1 over p times n over m, and since m is strictly greater than n, this is a number between 0 and 1. So, in particular, we have that q and p are different primes. Now, since q and p are different primes, and since p divides this product, since p is a prime, p has to divide this number or this number. But since p and q are different primes, this implies that p has to divide n. In a similar way, we have that q has to divide m. So we have that we can find m bar and n bar natural numbers such that n is equal to p times n bar and m is equal to q times m bar. Now, back into this equation, we have that p times q times m bar is equal to q times p times n bar. So we have that m bar is equal to n bar, and we can call this natural number k. So we have that n is equal to p times k and that m is equal to q times k. But now we got a contradiction, because if we go back here, for example, we have that 1 over q is equal to x over m, and this implies that x is equal to m over q. But now m is q times k, so we have that q times k over q is equal to x, but this is k. But this is a contradiction because x is in the open interval 0, 1 and k is a natural number. So this is not possible. The contradiction started here. So we have proved this. In other words, we have proved that this set is a set of this kind. And so our counterexample can be rewritten in this case. So we can write f of x to be equal to 1 if there is p prime such that x is equal to 1 over p and f of x is 0 otherwise. This was everything for this video and ciao to everyone!